You'll be very familiar with standing waves on strings. All stringed musical instruments make use of these standing waves to a greater or lesser extent. Now, we only get standing waves at specific frequencies, and each of these set of waves has a wavelength which we can express as a fraction of the wavelength. If we draw on our oscillator here, you can see that we have an antinode where there's a maximum displacement, and we have a node where there is no displacement. Okay? Now, in music, for example, on a guitar or a harp string, the lowest frequency note that is produced, which would look like this, is known as the fundamental frequency, and the higher frequencies are known as resonant frequencies. Now, this is a slightly complicated diagram, but you can see that at each end where the wave is fixed, there is a phase change. That's the node, no displacement. And the maximum amplitude, represented by A on this diagram, is called an antinode. Now, you can see that the distance between two nodes or between two antinodes is half a wavelength. The distance between a node and an antinode is a quarter of a wavelength. So, if the length of the string is L, then this will be equivalent to half the wavelength of the longest wavelength. So the wavelength we actually use is 2L. And there is for the first harmonic. Now, use the worksheet to draw the pattern of nodes and antinodes for higher frequencies and work out the resonant frequencies for waves on a string.